You are at the birthplace of our nation's nuclear energy, nuclear medicine, and our nuclear navy. You are looking at the face of the X-10 graphite reactor, formerly known as either the X-10 pile or the Clinton pile, just as it looked when it was decommissioned in 1963. This facility was designed by Eugene Wigner and Enrico Fermi and built by the DuPont Corporation as an air-cooled graphite moderated pilot plant, or semi-works, for the World War II Manhattan Project. During World War II, the X-10 reactor was operated by the University of Chicago. Construction began in February 1943 and completed in 9 months at a cost of $12 million. For the fission process to chain react, the neutrons created by the fissile uranium U-235 must be slowed down by interacting with a neutron moderator before they will be absorbed by other uranium atoms. The X-10 graphite reactor consists of a huge pile block of 4-inch by approximately 50-inch, 4+ feet, graphite logs, forming a 24-foot cube weighing about 1,500 tons, and surrounded by a 3-foot airspace for the air cooling and 7 feet of high-density concrete for shielding. It rests on a concrete pad that extends down to bedrock. The graphite logs have beveled edges, which result in the 1,248 diamond-shaped channels on 8-inch centers to accommodate the round fuel slugs of a uranium oxide. The fuel slugs are 4 inches long and 1 inch in diameter and weigh 2.5 pounds each. Each fuel slug is encased in an aluminum cladding to protect the uranium oxide metal from oxidation at the reactor's core temperature of between approximately 300 and 500 degrees Fahrenheit. Only about 800 of the available 1,248 channels were needed and used to produce the desired critical reaction. Between 24 and 54 fuel slugs were in each of the designated channels. Donut slugs were normal fuel slugs with a hole in the middle for insertion of materials for fast neutron exposure studies. The reactor, or pile, was controlled by 5 control rods of heavy elements, including boron and cadmium. X-10 workers began loading the uranium oxide slugs into the reactor during the afternoon of November 3, 1943, and the reactor went critical at 5 a.m. on November 4, 1943, with 44,000 uranium fuel slugs in the channels, weighing about 30 tons. A week later, the load was increased to 54 tons, and by the end of 2 months, December 1943, the first 2 grams of plutonium were created. Each fuel slug was used approximately 1 month, the time necessary for the neutrons absorbed by the U-238 isotope to create Pu-239, and, with the reactor shut down, pushed out the back of the reactor and into a trench of 20-foot deep water pit to cool and allowed to decay for several weeks. The fuel slugs were then moved underwater in the canal to the Chemical Separation Process Building, currently numbered as ORNL Building Number 3019, where they were dissolved in acid and the plutonium separated out. 4 technical and 15 non-technical men were needed to operate the reactor. The second floor of the reactor was used primarily for physics experiments, and third floor was used for biological experiments. The X-10 reactor became the training facility for all the Hanford reactor operators, and the X-10 graphite reactor's chemical separation facility became the model for the facilities built at the Hanford facility. The X-10 reactor operated as the initial production plant to produce minute quantities of Pu-239, shielding research, and the production of polonium-210 for nuclear weapons initiators until January 1945, approximately 14 months, when it was turned over to non-weapons research activities. In total, the X-10 graphite reactor produced just over 300 grams of plutonium for the war effort. February 2, 1945. Los Alamos received its first shipment of plutonium from Hanford. During the 20 years that the X-10 graphite reactor operated, from 1943 to 1963, it continued its pioneering role. It produced the first electricity from nuclear energy. It was the first reactor used to study the health hazards of radioactivity and research on radioactive shielding. And, for years after the war, it was the world's foremost source of radioisotopes for medicine, agriculture, industry, and other purposes.